Okay, so this slide here is a really important one to sort of have in front of you when you go through the next few practice problems. We try and give you a few sort of, again, main sort of helpers and key links to this. One of the things I just want to preference is that when you analyze pedigrees, nothing is ever 100%. Okay, so a lot of the times we say that sex linked cannot be confirmed. We essentially are looking at patterns. Okay, and once you kind of can prove patterns, you can usually be fairly comfortable. All the examples you're going to see are going to be confirmed types. So I actually try and give you the name of each disorder, whether it's red-green color blindness or vitamin D deficiency or hemophilia, etc. So again, this is part of your notes. Really important that you take a look at this and then use it as you apply and sort of practice the next few questions. Okay, for this practice problem, the first thing you want to check is it dominant versus recessive, and then see if you can find the pattern of autosomal versus sex-linked. So if you're looking at dominant versus recessive, always ask yourself, is there a generational skip? Okay, so if we take a look, there's an affected person on generation 1, we have several affected on generation 2, and many affected on generation 3. So we can almost assume that this is definitely dominant. And then if you look at the autosomal versus sex-linked, look at your circles to squares. I seem to have a much more prevalent circles to squares that seem to be affected. So right now we're kind of leaning towards the idea that it's a sex-linked. So that's the first job. Now you need to go in and see if you can confirm it. So one of the first things I'd recommend you do is look again at the affected individuals. So if I look at dad here, dad is affected, and I know if this is sex-linked, I'm going to start writing in the sex chromosomes. Now, because we have an affected dad producing both unaffected and affected children, let's take a look at what mom could be. So what we're going to do is we're going to kind of give ourselves a legend. We're going to say, if this is a dominant gene, we're going to say a capital A is affected. So you have this. And then we're going to say little a would be unaffected. It's a really good idea to actually have this in front of you, and so that you can kind of track it. So because dad is affected, we're going to give dad's genotype a capital. Because mom is unaffected, she would have to have 2 unaffected genes, so homozygous recessive. Now let's see if we can confirm it. So again, here's the best way to look at this. If this is a dominant trait, let's take a look at an unaffected individual. So I'm going to look at their firstborn son. So this is their second child, but the first little boy. Now I know from dad, the only thing he can get is the Y. Okay, so I know that that's why he is not affected, because this gene is not carried on the Y chromosome, which means the only thing he can get from mom would be her unaffected gene. So far this pattern holds in that because this is a dominant gene and because mom didn't have any affected, so far little boy isn't affected. Now let's take a look at any of the little girls who seem to have it. And again, because dad is producing affected girls, okay, this is the really big key here, because dad, who is affected, if you look at his daughters, okay, all his daughters are now affected. Think through why. Okay, so I think a lot of you have sort of figured it out, is because the only thing dad can give his daughters is his affected gene. So the fact that all of these little girls are affected, it's because dad's 1 X chromosome is the one that's carrying this affected gene. So far, we can almost confirm that this is going to be a sex-linked dominant. And what you can do is you can always go in and just double check and fill in the rest of your genotypes, okay? But so far, this pattern is holding. So to really confirm it, we can actually look at the one individual here, this one affected little girl who started to produce generation 3. Okay, so when we start again looking at her, I know that she got the affected gene from dad, and I know she got the unaffected gene from mom. Okay, she then met a nice guy who was unaffected, so he would have to have that little a. So when we take a look at their offspring, again, this is now making sense. So the key here is look at the boys. Okay, so one of the things, hopefully you can figure out why, is that I know that all of his sons, the only thing that they are getting from dad is the Y, whether you're affected or not. Okay, however, if I look at mom, this is where that probability, this is where, again, the roll of the dice. So if you needed to, you can easily create a Punnett square, and we can put mom along the top and dad along the bottom. And this is where, again, you can start to see these combinations coming through. So if I look at the little girls, I'm going to have, again, some that are affected, some that are not. But if I look at all the boys, all the little boys, again, have an option of either being affected or not. And that's exactly what we have. We have some that are affected, some that are not. So if I look at this affected little boy, he unfortunately got the affected gene from mom. So that is this little boy right here. But his second brother, I guess, this third little boy right here, he was luckier, and he then got the unaffected gene from mom. So we can definitely confirm that this is a sex-linked dominant, and this is actually a vitamin D deficiency, if you really wanted to know. So this is actually when your body cannot actually synthesize vitamin D. So I hope that helped. Greetings. So for problem number 2, again, give yourself step by step. So take a look, is it going to be dominant versus recessive? So again, ask yourself, is there a generational skip? So when I look through, it looks like I have an affected individual on generation 1, but then it skips generation 2, and then it comes back in generation 3. So we're looking right now that there's a skip, which is typically indicative of a recessive disorder. And then we're going to take a look at autosomal versus sex-linked. And currently, I only have little boys that are affected versus girls. So we're kind of looking at the fact, again, this might be a sex-linked. Okay, so now just give yourself a plan and see if the pattern's going to fit with your prediction. So the first thing you want to do is give yourself a key. So again, using letters, I'm going to say a capital A, because this is a recessive gene. If you're capital, you're going to be normal. You're not going to be affected, and little a would be affected. So that makes sense. Okay, the next thing you're going to do is now start to put in your prediction, okay, and then put it into play. So now that we think that this is sex-linked, I'm going to obviously write in my sex chromosomes, okay, and I'm going to start with generation 1. Now, because dad is affected, we're going to assume his 1X chromosome is going to be a little a. Now, again, I'm only ever focusing that these are X-linked because when you look at the fact that if this was a Y-linked, he would have every one of his sons affected, and they are not. So we're pretty sure that even though when we say sex-linked, we really mean they're X-linked. Okay, it's pretty obvious when it's a Y-linked. When we now look at mom doesn't have this, so now we have this question. Is mom homozygous dominant, or is she going to be is she going to be a carrier? And this is one thing we have to kind of predict. We have to look for, okay? So when we start looking at her offspring, again, you can even set up a Punnett square. When you take a look, and this pedigree is really important, only focus on their children. So in generation 2, we're only going to look at individual 2, 3, and 5. I'm almost going to ignore right now their mates or their spouses because I don't want to dilute this. So I'm going to take a look on generation 2, individual 2. This is the key because they are the only group that are producing an affected son. So this is where we can start to unpack. So what I would do is I'd actually start and I'd move backwards. I'm going to take a look at the son. I know that this little boy has this disorder. So I know that his genotype is just like his grandfather, who's going to be little x, who's affected with that recessive gene and the Y. So if we take a look at mom, okay, again, so this is individual 2 on generation 2, we have to figure out what her genotypes are. Now I know if we look at her direct father, the only thing that she got from her dad is going to be little a. We know that. Now for mom, we have to figure out what she got from mom. Now again, because they have an affected little boy, okay, this is where you have to start to dig through. So let's take a look at individual 2, generation 1. I know that this dad is unaffected, so I know that they are going to get big A, okay? Now again, if I take a look at their affected son, the only thing that he gave his son was the Y. So when you look at this, their affected child, so individual 2 on generation 3, that little a had to come from mom, okay? So I now know that mom had to at least have one little a, but because she's unaffected, that would mean her other gene would have to be a big A, Okay, so I hope this makes sense. We can unequivocally say that generation 2, we know that their parents, dad's going to be capital A, and we know that mom is going to be heterozygous or carrier. And apologize, I did write those two backwards. But then when you then trace back, again, I cannot say for certain sort of this maternal grandmother on this pedigree, if again she was dominant, homozygous dominant, or if she was a carrier. There's really no way for us to know, but if we kind of look predictively, the fact that all of her children, again, both male and female, were unaffected, it's probably likelihood that she was homozygous dominant, but again, you can never find out, but that's okay. You can just look again at the affected individuals and go from there. I hope that helped. And for those of you wanting to know what this disorder is, this is red-green color blindness. So this, again, is something that is carried very much on the X chromosome. So this is if you are colorblind in the red-green. All right, so as always, you want to figure out, is it going to be dominant versus recessive? And the fact that you have 2 generational skips, pretty confident that this is going to be a recessive gene. And if you find, again, is it autosomal versus that sex-linked, the fact that we only have affected boys, we can almost be convinced it's going to be sex-linked, and specifically it's going to be X-linked. Because again, if it was Y, you would have affected males only producing affected sons, and that's not the case here. So now you can go in, and just to kind of prove, we think this is going to be an X-linked recessive, and it actually is. This is actually for hemophilia, but we can prove this. And again, when you start looking at who is who, if we look at mom, the fact that she is unaffected, we know that she is going to be at least have one dominant normal allele. So again, capital means normal, and that means a lowercase means affected. And if it's recessive, I gotta have both, right? So if we look at mom, we know that she is unaffected. If we look at dad, we know that he is unaffected, so he has to get the capital. Now, the one thing we don't know about mom is what is her other gene. So, and again, you take a look at the affected kids. So we know that the affected little boys, the only thing they're going to get from dad is the Y, but because they are affected, that means they had to get an affected gene from mom, and so that means they had to get that little A, and the only person who could do that would be from mom. So we now know that mom must be a carrier because she produced affected boys. Now, there were also a few children who were unaffected, and that just means that they would have received that unaffected allele from mom. And again, you can see that Punnett square. So when we take a look at sort of generation number 3 here, when again, we see more affected children, I know that the sort of the father to this generation had to be unaffected because he is not colored in. But again, if we take a look at mom, we know that she was unaffected. So thanks to dad, she would have gotten dad's unaffected gene, but she was a carrier, and we know that because she again produced affected boys. Right. So again, I know that this is the case, and then when you take a look at the last generation, this mom on that last generation, again, obviously she had to be unaffected, so she had to have again that capital, and the fact that her husband, we know, got that affected allele from their mom, and the fact that all of their children are unaffected, one of the things we can't say for certain, is this a mom, is she homozygous dominant, or is she, again, a carrier? We can't be for certain, but the fact that both of her boys are unaffected, there's a good chance that she was probably homozygous dominant, but again, it could have just been the luck of the draw, and that both of these little boys could have got just that unaffected allele. But we can't say for certain, and that's why we would leave this individual as both. So I hope that helped. So again, this is basically hemophilia. So again, that is a sex-linked trait carried on the X chromosome. All right, this is practice problem 4. So I actually was a little bit helpful here. I actually told you what this trait was. So I said that this was an autosomal recessive trait. So right away, please give yourself a sort of a key to this. So because it's autosomal recessive, I don't have to worry about X's and Y's, but I do know that if you have 2 lowercase letters, you are affected. So I'm just going to use the letter A's just because they're easier to see, which means I can either be homozygous dominant to be normal or unaffected, or I can be heterozygous, so big A, little a, but I'm also normal. But again, you would be a carrier for this. So when you take a look, what I would suggest you do is write in what you know. So currently, I have 3 affected individuals. I know that their genotypes have to be little a, little a. I know that, okay? So that's the easiest thing to do. Everyone else who's unaffected, they can either be homozygous dominant or they can be heterozygous. So this question specifically asks for individual 1 on generation 3. So that's on generation 3. So I'm looking basically at this little boy, this man, and his wife, and they produced 2 affected kids and then 1 unaffected child. So when we start to take a look and you unpack it, the fact that both of these kids had a little a means that one of these little a's from their first daughter had to come from dad, and the other little a had to come from mom. Okay, so we both know that they had to at least carry this affected allele. We know that. And the same thing with their firstborn son. But their daughter is the key. So remember, she is unaffected. So is she, again, capital A, little a, or does she have 2 capitals? Well, the fact that she has siblings who are affected, we can almost guarantee that she won't have 2 big A's, because she was lucky enough to get a big A from someone. So we know that one of these individuals have to be at least carry 1 big A, but because they're both unaffected, they both have to have that big A, okay? That's the only way that they produce both affected and unaffected children. Okay, so I hope that helps. All right, so again, for this question, just sort of get yourself set up. So we have a child who is blood type A. So I'm just going to stop there. So that means I know that there are 2 possible genotypes. They're either going to be homozygous dominant, or they're going to be heterozygous for this blood type. So now I need to figure out what are all the possible blood types of its parents, and then we need to show each cross. So what you can kind of do is you can almost go in and fill in what you know. So I know, say in this first one, if I were to create that homozygous dominant trait, that would mean that both parents would need to be homozygous dominant. Okay, so that's an easy one to fill in because I know that in order to produce 2 of the same, I know that one parent, or each parent, would have to be homozygous dominant. Okay, so we would need both. So then the next thing we could look at is, well, how do I get the heterozygous? Well, again, I could have one parent who is homozygous dominant, and I could have another parent who is heterozygous. And again, I'm still going to get that first prediction, but I'm also going to get this heterozygous. But so this person is still going to present as type A, but they'll be heterozygous. So now I know that I could also have a parent who is heterozygous. Now the third one, okay, is sort of the next one, where again I could have a homozygous dominant or even a heterozygous. It doesn't matter, but we know that one parent has to have this dominant A, and they can actually be crossed with someone who is type O. And you're still going to produce type A children because, again, that dominant gene. Okay, all of these kids would still be type A, but they would be heterozygous. So the other parent could also be homozygous recessive. So I hope that helps. And yeah, it's a great one. I could even do a 4th cross if I wanted to, and replace this one individual here with, again, it could be a heterozygous cross, but we already included that individual. And the only thing that that would show is that your likelihood then of having a blood type O would be 50%. But in this question, their child has blood type A, so they're only the ones who are going to be the ones who have that dominant A. So I hope that helps. All right, so this is the last practice problem we'll take you through. So now we're dealing with color blindness. So we already actually know that, and this is what's good to have in your back pocket, that color blindness is an X-linked trait, and we know that this is actually recessive. Now, you can still do this question even if you didn't know this. And so if we take a look, we have Janet and Wayne. They're expecting a baby. They both have normal vision, but their fathers are colorblind. So again, if you kind of take a look and you plan this out, the fact that they are unaffected, but they had affected parents, lets you know that this, again, was recessive because they are the generational skip. And so if you're not quite sure, is it X or Y linked, the fact that, again, if it's Y linked, it would only be on boys. Okay, so we can almost be rest assured that this is going to be an X-linked. So when we take a look at what Janet's potential genotypes are, if we know that this is a sex-linked, we're going to give mum, obviously, 2 X's. Now let's take a look at this. Mum is unaffected. So the fact that she is normal, she's going to get at least 1 capital A, because this means that she's normal. Now, she can either have 2 capital A's, or she might again be a carrier. And again, we can actually determine what she is based on the fact that her father is colorblind, so that we know that her father would have had this one affected allele, and this is the allele that he would have given to his daughter. So we know for certain that Janet would need to be heterozygous, okay? So we can actually put Janet within our Punnett square very confidently. And then we take a look at Dad. So if we take a look at Wayne, okay, he again is unaffected. So as a man, to be unaffected or to be normal, his only X that he carries has to be a capital A. Okay, because even though his father might have been affected, if you again take a look, his dad would have had a small x little y. The only thing that Wayne's father gave to him was this Y chromosome, which means he got this normal dominant allele from his mom. So again, we are very confident that Wayne is going to be a normal unaffected. So now when you do your cross, okay, and you fill everyone in, I then get 2 little girls. 50-50 chance as far as who is homozygous dominant and who's a carrier, but I'm going to get no little girls that are your XX that are going to have this combination. I'm not going to get a little girl who's homozygous recessive, so there's a 0% chance for that. And now if we look at little boys, little boy number 1 is going to be normal, thanks to mum, but little boy number 2, again, thanks to mum, could have this. So again, when you take a look at your probability, this is a boy with normal vision, okay? So we're looking at this young man. When you take a look at your probability, consider this with it as an and. So again, to kind of go through, if you look at the fact that he's a boy, that's a 0.5% chance, and you look that he is normal. Again, out of the ones that are normal as far as a boy, again, he's got a 50-50 chance of this. So when you multiply those two together, you're going to get 0.25. Or to simplify that, the fact that this is 1 out of 4 within the whole Punnett square, this is a 25% chance that this little boy will be normal. And I hope that helped. All right, welcome everybody. Here's basically how you work through our baby mix-up question. So when you take a look, if I focus mainly on the Frisbees first, because they're actually the most complicated group, if I look out their potential genotypes, being that Mr. Frisbee is blood type A, we don't know if he's homozygous or heterozygous, so we'd have to assume that he could be both. And Mrs. Frisbee being blood type B, again, she could be homozygous to B or heterozygous. So when you do that cross, they actually can produce every potential phenotype. So we're going to leave the Frisbees for now, but right now they seem to be the only ones that are able to produce this AB. So I just want to leave that sort of to the side, but because they could produce a blood type O, they also can produce a blood type B. We're just going to leave the Frisbees off to the side, and let's take a look at the Zimmermans. So if we look at the Zimmermans, they're the easiest ones. Because they are only blood type O, they're only going to be, again, that homozygous recessive. So they can only produce blood type O. So we can almost for sure know that Dominic here is baby to the Zimmermans. So we know that Dominic is only the Zimmermans, which means if we go back to the Frisbees, we can cross out them as the blood type O, because the Zimmermans are the only ones that can produce a blood type O baby. Okay. Now, if we take a look at the laws, again, they're a little bit more complicated. So if we look at the laws, again, we have Mr. Law, who is AB, so he's going to be codominant for that blood type, and Mrs. Law is going to be homozygous recessive. So again, if we take a look at their crosses, they could produce Tommy, who is our blood type B baby, okay, because this is our blood type B, but they could also produce a blood type A. But because there's no blood type A babies in the list, again, we can then be pretty confident that Tommy is going to belong to the Laws, because that is the blood type B. Okay, they're the only ones who can produce that. But again, if we take a look at the Frisbees, they also had a blood type B, but if we look who's left, Kristen, she's the only AB baby. So we can assume that the Frisbees were not the people with the blood type B, because the only family who could produce the AB baby is going to be the Frisbees. Okay, so I hope that helps. That's a good little question, one that I think might show up a little bit later. So hope that helped.